In this experiment, we're going to be determining the change in enthalpy for a neutralization reaction. So you will be assigned an acid and everyone will be using sodium hydroxide as the base. Remember that enthalpy change is delta H, and the delta means the change, and H is what we use for enthalpy. And enthalpy is a measure of heat at constant pressure. So chemical reactions are classified into one or another. We have two groups, endothermic reactions and exothermic reactions. Endothermic reactions are those reactions that absorb energy or heat in order for that reaction to happen. Exothermic reactions are the type of reaction that are actually releasing heat. So when you have your reaction, the reaction is the system, and then everything around your reaction, including the solution containing the chemicals that are actually reacting, are the surroundings. So if you have an endothermic reaction, endothermic reactions will have a change in enthalpy that is a positive number. When you have exothermic, the change in enthalpy will be a negative number. So remember, we're looking at the reaction as your system, and then the solution will be the surroundings. So the exchange of heat will happen between your surroundings and the solution. That will be ideal, but the heat can be transferred also to, for example, the cup containing your reaction. So if you have an endothermic reaction, right, your reaction needs to absorb heat. The heat that that reaction will be absorbing will coming from the solution. Okay? So in my sketch, I have my reaction in a yellow box. That's your actual reaction, right? That it's happening in the solution. Now, the red arrows represents the heat transfer. So heat will be absorbed by the reaction. So that heat is coming from the solution, which is what the reaction is in contact with. Now, on the right side, you have your exothermic. For exothermic reactions, you have a change in enthalpy, which is a negative number. It's a negative number because of what's happening to the heat transfer. Your final amount of heat for the reaction is smaller than the initial, and that's how you get a negative, because the change in enthalpy is final minus initial. So if the final is smaller, you will get a negative value. So I have my reaction in a blue box. Okay? So that represents my reaction that it's happening in the solution. If heat is coming off from the reaction, right, the heat will move. The red arrows are pointing from the reaction towards the solution, because the heat that is being released by the reaction, it's moving towards the solution. So the temperature for your solution will be increasing. Right? The temperature of the solution is what we can actually measure. And that temperature will be increasing because the heat from the reaction is moving towards the solution, increasing the temperature of the solution. The contrary is happening on your endothermic reactions. Since the reaction is actually absorbing heat from the solution, the temperature of your solution, the one that you can measure, will be decreasing, right? Because the reaction is absorbing the heat. So when you're performing this experiment, you're going to be using a calorimeter. The calorimeter is just a coffee cup. So we have two coffee cups, one smaller inside of a bigger one. So everything, the solutions will go inside the smaller cup that is inside the bigger one. So your coffee cup, it's isolating the heat, right? It's inside, and we're trying to avoid for any amount of heat to be lost to the outside of your coffee cup. So any temperature changes that we're measuring are coming from everything that is happening in your solution. But ideally, right, we will expect for the heat transfer to happen between solution and reaction, and that's it. But your coffee cup will absorb some of that heat. So the first part of the experiment, we're going to be calibrating the coffee cup that we're using to determine the change in enthalpy for the reaction in the next part. So in that part, we're using just water, hot and cool water, just to check the heat transfer, and we're going to calculate how much of that heat is actually absorbed by the calorimeter. And with that, we're going to be finding out the heat capacity of your calorimeter, or calorimeter constant. And then once we have that number, we can use that number in our calculations for the change in enthalpy for the actual reaction. So for your procedure, we're starting with the part where we are calibrating the coffee cup. So measure 50 milliliters of distilled water using a graduated cylinder. Transfer those 50 milliliters of distilled water into a beaker, and now use a hot plate to warm that water. So check like about the temperature at room temperature, like let's assume that it's around 20, so you can check the temperature of your thermometer. And now you're going to heat up the water until that temperature increases by about 15. So if you start at room temperature with a temperature of 20 plus 15, that will give you something around 35. Okay? So while you're waiting for the water to warm, you can start doing the cool water part. So for your cool water, you're measuring again 50 milliliters of the cool water, and you're transferring those into the coffee cup in your calorimeter. So while one student is watching the hot water, another student can be determining the temperature of your cool water every 30 seconds for 2 minutes. So you pour your cool water or water at room temperature into your coffee cup, and you use the thermometer to check the temperature. Okay, at 30 seconds, this is the temperature, and then another 30 seconds, 60, and write down the temperature. And you have to do that 4 times until you are at 120 seconds. Once your hot water reaches like the temperature that you're looking for, like 15 degrees above room temperature, you can remove it from the hot plate. Sometimes once you remove the hot water from the hot plate, the temperature keeps increasing. That is fine. So you're going to do the same thing now with the hot water. Use the thermometer and write down the temperature every 30 seconds for 2 minutes. So at 30 seconds, copy the temperature. 60, copy. 90, copy the temperature. And then 120, copy the temperature. Once you have your measurements for time and temperature for the hot water, you're going to transfer the hot water as quickly as possible into the coffee cup containing the cool water. Cover the calorimeter immediately, and you will have a copper wire and your thermometer. Copper wire is for stirring, and the thermometer is for determining the temperature now of a mixture, hot and cool water inside the calorimeter. So you're starting to determine the temperature, and that time right now is not at 120. 120 seconds is when you're finishing measuring the temperature of your hot water, right? Every 30 seconds. So now immediately after that, you're transferring the hot water into your calorimeter. Cover, stir, and now 30 seconds after, you're going to determine the temperature. So that's the first temperature that you have for the mixture of your hot and the cool water together in the coffee cup. Another 30 seconds, copy the temperature, and you're going to keep copying the temperature of your mixture, hot and cool water, until thermal equilibrium is reached. So remember, thermal equilibrium will happen when the temperature of the hot water, right? Heat always moves from hot to cool. So the hot water will be transferring heat into the cool water. The temperature of your hot water will start decreasing. the temperature of your cool water will start increasing until you have the same temperature for both. That's thermal equilibrium, and whenever that happens, the temperature will remain constant. So you don't have to wait until the temperature goes down to room temperature. Okay? You have to wait until the temperature remains constant for a couple of times. So if you see that your temperature after 210 seconds, it's let's say 30 degrees, and then 240 seconds is also 30 degrees, and you have like 3 measurements that are exactly the same temperature, you can assume that that's thermal equilibrium and you're done. You're done recording time and temperature. Once you're done with this, you have to repeat everything again. You're measuring 50 milliliters of distilled water. You're heating up those 50 milliliters of distilled water, and now use a different temperature from the initial one. If you warm up the water to 35, then this time warm up the water to 45 or something like that. Try not to use the same one. And also 50 milliliters of distilled water in the calorimeter. Determine the temperature of your distilled water in the calorimeter every 30 seconds for 2 minutes. Warm up the water, remove from the hot plate. Determine the temperature of the hot water every 30 seconds for 2 minutes. Very quickly transfer the hot water inside the calorimeter with the cool water. Cover, stir, and determine the temperature again every 30 seconds until you reach thermal equilibrium. So you're doing the same thing twice. Now the next part is where we're actually mixing chemicals to have our neutralization reaction, so we can calculate the delta H for that neutralization reaction. So for this part, the volumes of solutions that we're using, we're going to measure using burettes. So you have 2 burettes, one for the acid, one for the sodium hydroxide. Make sure that you put a labeling tape, or that you are 100% sure in which burette you have the acid and in which one you have the base. So the burette containing the sodium hydroxide, which is the base, you're going to fill your burette as we do, right above the line for 0. After the burette is cleaned, you add your sodium hydroxide above the line of 0, and then you drain the burette down to 0. So you have in your burette all 50 milliliters of sodium hydroxide. And then in the other burette, you're going to add the acid. So clean burette, and now you're adding the acid above your line for 0, and then you're draining your burette down to 0, so you can have your 50 milliliters. The base that you have in your burette, you're going to transfer into a coffee cup. Okay? So you're transferring the 50 milliliters. So make sure that you don't empty the burette, that you look at the scale in your burette from 0 down to 50. So from 0 to 50, you're going to transfer that into your calorimeter. And then for the acid, you're going to do the same thing. From 0 to 50 in a beaker. For the base, okay, that you have in your calorimeter that you measure using the burette, you're going to determine the temperature every 30 seconds for 120 seconds, okay, which is 2 minutes. So every 30 seconds for 2 minutes, you're writing down the time and the temperature. Now you have your beaker containing the acid, and you're going to pour the acid very quickly into the calorimeter. You're going to cover the calorimeter, stir, and now determine the temperature every 30 seconds, okay, for 5 minutes. That will be more than enough time for the temperature to reach thermal equilibrium. So you will notice that the last few temperatures that you're getting will be the same, because the reaction reach thermal equilibrium. So the acid goes into the calorimeter containing the sodium hydroxide. Make sure that when you do your transfer that you cover everything very quickly. We don't want any heat to escape the coffee cup. So transfer the acid very quickly, cover the calorimeter, stir, and determine the temperature. And again, the temperature, right? You're finishing determining the temperature of the base inside the calorimeter at 120 seconds. So now you're adding the acid, and that next measurement will be 120 plus 30 seconds, right? Every 30 seconds. So the first one will be 150 seconds. And you keep adding your 30 seconds until you are at 5 minutes. Once you finish with everything, you can pour everything in the waste container, and you have to repeat the same thing once again. So we're doing 2 trials for everything, to determine the calorimeter constant and also to determine the delta H for the reaction. So we do 2 trials, and then we calculate the average of both, of using both trials for part 1 and for part 2.